All right, this is the last problem that we have that's going to be only in the vertical direction instead of just dropping it or throwing it down. Now we're saying we threw the ball up in the air and what can we calculate? So in this problem, it talks about weather's getting nice, which it is, which is awesome. And you get outside and you start throwing the ball up and down. And you're able to figure out that you threw the ball up at 25 meters per second. All right, and then we can start calculating some different things that it asks for. All right, so again, we're working just in the y direction. And so what things do we know right off the bat? Same as always, in the y direction, our acceleration is -10. That is always going to be the case in the y direction while you're here on Earth. Okay, that could change if you go to another planet, but here on Earth is always -10. All right, in the problem, it tells me that you were throwing the ball up in the air at 25 meters per second. Now this is positive because again, up is positive, down is negative. That's the sign convention we've had for every unit so far this year, and that hasn't changed. So throwing the ball up in the air is positive 25. On a previous problem, when we threw the ball down, it was -10. All right, so this time positive because it's upwards of 25 meters per second. All right, so it asks us to find a couple different things. It asks us to find the time at the peak, how high it actually travels, the velocity at 4 seconds, and the velocity when you actually catch it. So let's start with that first one. What is the time it takes to get to the peak? All right, that is not 4 seconds. There is a time given, but that is asking specifically for the velocity at this time, not that this is the time of the peak. So don't confuse 4 seconds with this answer. You have to actually calculate this out. All right, so we take a look here and we go through and we realize, wait a minute, I only have 2 values. There's nothing here that only has 3. Okay, so I need to have 3 values in order to solve for the 4th. So I'm stuck right off the bat. What this should tell you is, all right, maybe there's something I'm not thinking about that can actually give me a value. Well, we're trying to find the time at the peak. All right, just do a little subscript of peak so I can keep track of what this number actually represents. And so what do I know about the motion of the object at the peak? So if I have any object here, all right, and I'm just tossing it up and down, okay, it comes back down, right? So this is similar to the problem we're talking about. Throw the ball up, hits its peak, comes back down. Now, if I could stop this ball, or this apple, or whatever this is, right at the peak for that instant before it started coming back down, how fast is it actually going? Well, it's actually not moving for that fraction of a second. It's as if the velocity is 0. So I could use that to help me. I can say, all right, the velocity, all right, to the peak, I'm not sure, but the velocity at the peak equals 0. So I could use this velocity as a final velocity to help me. So I take a look and say, all right, time at the peak, I have an initial velocity of 25. Then I know it's 0 here. I could actually use this first equation to solve for my time to the peak. So my final velocity at the peak is going to be 0. My initial velocity is 25. My acceleration is -10. And t is what we're solving for. All right, do a little algebra. That cancels. I'm going to divide by -10 on each side to equal t. These negatives will cancel themselves out. 25 divided by 10, t equals 2.5 seconds. So t to the peak is 2.5 seconds. All right. So it's a good thing we didn't put 4 seconds in because that wouldn't have been correct. And now we have a time to the peak. The next question is, how high did the ball travel? So you have it in your hand, throw it. What is the displacement vertically from where I let go to the peak where it started to come back down? So I'm trying to find my displacement. Well, I have 3 values now. All right, so let's see if the equation that we typically use for this, or use most often, will work. All right, well, I have an initial velocity of 25. I actually do have a time of 2.5. 1/2 -10 times 2.5 squared. All right, so 25 times 2 is 50. Half of 25 is 12.5. Add those together, I get 62.5 meters. All right, 25 squared will give me 6.25. Makes sense because 25 squared is 625. With the decimal place, it's going to move it 2 spaces. 62 or 6.25 times negative 10 gives me negative 62.5, or 0.25 rather. And then half of that gives me negative 31.25. Add those things together. The displacement is then 31.25 meters to the peak. So that's how we figure out how high this thing actually traveled. The next question asked us is, what is the velocity at 4 seconds? So we want to know specifically what the velocity is at 4 seconds. So that is the final velocity. So let's see if this one will work for us. It should. All right, our final velocity equals our initial velocity of 25 plus negative 10 times 4. This becomes 25 plus negative 40, or this equals negative 15 meters per second. So the velocity at 4 seconds is negative 15 meters per second. All right. So we have one more question of how fast is it traveling right before you catch it. All right, you threw it up in the air, went up, traveled down, came back, and I caught it. How fast is it actually going? All right, now this takes a little bit of understanding. There's some ways you can algebraically do this, but the biggest key is that the time to the peak equals 1/2 of the total time. All that means is time up equals time down. So if I know it took 2.5 seconds to go up, then it took 2.5 seconds to come down. Add those together, and it took me 5 seconds to travel all the way up and all the way back down. So I just use that same equation I just used, and I get 25 plus negative 10 times 5, and this gives me negative 25 meters per second. So the other thing that is consistent about these up and down problems is the velocity going up equals the velocity coming down. Meaning the velocity that I throw it up at, that initial velocity, will equal the final velocity right when I catch it, just opposite. Meaning, if this was 25 meters per second, this would be negative 25 meters per second, just like we saw here. So that's something that, and even knowing that, can bypass that step, but it's always good to go and check it out. So these are the 3 problems that are vertical only. The next problem is going to be a cliff problem where we have X components and Y components. So we'll solve for that, and you'll see how it might be a little bit different.